Can you identify the correct representation of classification in the given pictures? You have already learnt that classification is a type of supervised learning in which computers group together based on predetermined characteristics. Classification is an important tool in today's world where big data is used to make all kinds of decisions in government, economics, medicine, and more. Researchers have access to huge amounts of data, and classification is one tool that helps them to make sense of the data and find patterns. Let us learn more about the classification process through this interesting example. Most golfers prefer to play when the weather and outlook conditions meet certain requirements. Despite the outlook being sunny, too hot or too humid conditions are not preferred. On the other hand, overcast skies with cool temperature pose no problem for playing. Based on the past records of these conditions and preferences and information about a day's temperature, humidity level and outlook, classification will allow us to predict if a person will prefer to play golf or not. These are called predictors. The predictors can be continuous, such as temperature and humidity, or categorical, such as sunny, cloudy, windy, etc. The outcome of classification would be to categorize the weather conditions when golf is likely to be played or not, quite simply play or not play. There are a number of techniques available to handle and solve such classification problems. In this section, you will become familiar with the working of three most commonly used techniques: decision trees, k-nearest neighbor or KNN, and support vector machine or SVM. Tools like R, Python, which come packaged with pre-built codes, are used to apply these techniques on datasets. As a programmer, you may not be required to understand the internal working of these pre-built codes, but it is always better to know about how a technique works in order to appreciate its application. Decision trees are popular among the spontaneous and frequently used data mining techniques. They are easy to set up and interpret and hence are preferred by analysts as well as business users alike. Decision trees are used to separate a data set into classes belonging to the response variable. That is why these are also known as classification trees. Typically, the response variable has two classes, yes or no, which is 1 or 0. But there may be cases where the response variable has more than two categories. In such cases, variants of decision trees are popular among the spontaneous and frequently used data mining techniques. They are easy to set up and interpret and hence are preferred by analysts as well as business users alike. Decision trees are used to separate a data set into classes belonging to the response variable. That is why these are also known as classification trees. Typically, the response variable has two classes, yes or no, which is 1 or 0. But there may be cases where the response variable has more than two categories. In such cases, variants of decision tree algorithm may be applied. How do decision trees work? In order to understand this, first you need to learn about the concept of impurity of a class. Suppose you have a set of data as illustrated in the diagram where two classes are represented by red circles and green squares. As the set contains data belonging to different classes, it is not 100% pure. Now divide this set of data into two subsets with the help of a blue line. Here, both the subsets have data belonging to a single class and thus both subsets are now 100% pure. This implies that a data set is impure when there are traces of one class division in the other class. The amount of impurity of a data set is at the maximum level when all possible classes are equally represented, and it is 0 when only one class is represented. There are several mathematical measures such as entropy, Gini index, etc. to calculate this impurity. In this section, you will use the concept of entropy, formula of which is H is equal to minus summation Pk log 2 Pk, where K is equal to 1, 2, 3 up till M, which represents the M number of classes of the target variable. Pk represents the proportion of samples that belong to the class K. Using the attributes, decision tree model tries to create such subsets of the training data in which the impurity is as less as possible. The root to these subsets is then used for predicting the class of any new data point. Refer to the example of the golf data set to understand the application of entropy concepts for creating a decision tree. Suppose you are given data related to playing golf on various conditions. From the given data, take the outcomes as n, n, y, 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 n, y, n, where y means yes and n means no. Probability of y is equal to py is equal to 0.5. Probability of n is equal to pn is equal to 0.5. Entropy at this root node is H is equal to minus py multiplied by log 2 py plus pn multiplied by log 2 pn, which is equal to minus 0.5 multiplied by log 2 0.5 plus 0.5 multiplied by log 2 0.5, which is equal to 1. Divide the data set on the basis of various predictors: outlook, temperature, humidity, and windy. Calculate the entropy in each case. If you consider the outlook predictor, the combinations are 3 out of 8 cases are rainy, which means n, entropy is equal to 0. 2 out of 8 cases are overcast, which means y, entropy is equal to 0. 3 out of 8 cases are sunny, which means yn, entropy is equal to 0.918. Therefore, the overall entropy for outlook predictor using weighted average is 3 by 8 multiplied by 0 plus 2 by 8 multiplied by 0 plus 3 by 8 multiplied by 0.918, which is equal to 0.344. If you recall, entropy at the root was 1. Based on the outlook predictor, entropy is 0.344. Thus, reduction of entropy is equal to 1 minus 0.344, which is equal to 0.656. This is the information gain you get by dividing the data set on outlook predictor. Similarly, we can calculate the information gain for the other predictors. The predictor amounting to the maximum information gain is selected to divide the dataset. Continue this exercise till no predictor satisfies a minimum information gain threshold. A maximum depth is reached. As the tree grows big, not only does the interpretation get tougher, but you can run into a situation called overfitting. There are less than a certain number of examples in the current subtree to prevent overfitting. What is overfitting? Overfitting occurs when a model tries to memorize the training data instead of generalizing the relationship between the inputs and output variables. Overfitting often performs very well on the training data set but performs poorly on any new data. As mentioned, if overfitting occurs in a decision tree, the model thus developed is not only difficult to interpret, but it also proves to be a useless model for unseen data. In order to prevent overfitting, you may need to restrict the tree growth or reduce it using a process called pruning. Following these steps, you get a decision tree as shown in the diagram. Now consider a new situation where the weather condition is outlook is rainy, temperature is cool, humidity is high, and windy is false. Should you play golf? Flowing down the tree according to the result, first check the predictor rainy. The answer is no. You should not play golf. This is how the decision tree model works by creating and updating the flow with every new training data to predict the class as per the past pattern. KNN algorithm is associated with laziness. It is an example of a lazy learner model. When a large number of training data samples along with their independent features and levels are fed, it stores all of it in the memory, or rather plots the data in an n-dimensional space on the basis of its features. Hence, every sample is represented by a certain point in this plot. These are colored or marked to indicate their label. Take a simple case of two-attribute dataset to understand this algorithm. There is a spread of red circles RC and green squares GS, which are two output classes on these two attributes. You need to identify the class of the blue star BS. BS can either be RC or GS or not belong to either of these. The K in KNN algorithm is the nearest neighbor whose vote is to be considered. If you take K is equal to 3, you will need to make a circle with BS in the center. The circle should be big enough to enclose only 3 data points on the plane. Here, all the 3 closest points to BS are RC. Hence, you may safely conclude that the BS should belong to the class RC. Here, the choice became very obvious as all 3 votes from the closest neighbor came from the same class RC. If you take K is equal to 1, then the nearest neighbor of the test data point will be considered and the output class will be predicted as the output class of that neighbor. What if the closest training record is an outlier with the incorrect class in the training set? In that case, all the unleveled test records near the outlier will get wrongly classified. In order to prevent this misclassification, you need to increase the value of K to say 3. When K is equal to 3, you will consider the nearest 3 training records instead of 1. Since the class of the target record is evaluated by voting, K is usually assigned an odd number for a 2-class problem. There are various measures to find out the closeness of test data point with other data points. These are called measures of proximity, and they include techniques such as calculating distance, correlation, Jacquard similarity and cosine similarity. Here you will come to know about the distance measure. The distance between 2 points x1, y1 and x2, y2 in a two-dimensional space can be calculated as distance d is equal to square root x1 minus x2 whole square plus y1 minus y2 whole square. You can generalize this two-dimensional distance formula for n-dimensional space where x coordinates are x1, x2 up till xn and y coordinates are y1, y2 up till yn as distance d is equal to square root x1 minus x2 whole square plus y1 minus y2 whole square up till xn minus 1 minus xn whole square plus yn minus 1 minus yn whole square. For example, distance between the 2 points 1, 2 and 3, 1 in a two-dimensional space will be square root 1 minus 3 whole square plus 2 minus 1 whole square, which is equal to 2.7. This is called Euclidean distance. There are other distance measures as well, like Manhattan distance and Chebyshev distance. Among these, Euclidean distance is the most commonly used distance measure. The training data is plotted in an n-dimensional space. Whenever a test data is to be predicted, the model finds the nearest k neighbors based on the predetermined measure of proximity, generally Euclidean distance, and suggests the class of the test data as the majority class of those neighbors. Sometimes weights are assigned to the neighbors. When k is more than 1, it can be argued that the closer neighbors should have more influence in the outcome of the predicted target class than the neighbors who are far away. This can be accomplished by assigning weights for all the neighbors, with the weights increasing as the neighbors get closer to the data point. The weights are included in the final multi-voting step, where the predicted class is calculated. The term support vector machine is very much a misnomer for a predictive analytics algorithm, as there is no specified hardware. It is a powerful algorithm that has been very successful in applications ranging from pattern recognition to text mining. SVM works on the principle of fitting a boundary to a region of points that belong to one class. Once a boundary is fitted, you simply need to check whether a new data point lies inside the boundary or not. The advantage of an SVM is that once a boundary is established, most of the training data becomes redundant. All it requires is a core set of points that helps in identifying and fixing the boundary. These data points are called support vectors because they support the boundary. Why are they called vectors? This is because each data point or observation is a vector, which means that it is a row of data containing values for a number of different attributes. Take a look at this example to understand how support vector machines work. Imagine you have two tags, red and blue, and each tag has two features, x and y coordinates. For a new pair of coordinates, you require a classifier that would predict whether the given coordinate would be a red tag or blue tag. At first, you plot your labeled training data on a plane. A support vector machine takes these data points and outputs the hyperplane that best separates the tags. This hyperplane would simply be a line in 2 dimensions. This line is the decision boundary. Depending on which side of the boundary does a data point fall, it can be classified as a red or blue tag. What exactly qualifies as the best hyperplane? It is the one that maximizes the margins from both the tags. In other words, the distance between the best hyperplane and the nearest element of each tag is the largest. This example is easy as the data is linearly separable. A straight line is easily drawn to separate the red and blue tags. Usually, situations are not so simple. Take a look at this case. It is evident that a linear decision boundary cannot be drawn. However, the vectors are clearly segregated and it appears to be easy to separate them. How do you separate the vectors? You add a third dimension. In the earlier example, there were 2 dimensions, x and y. Create a new dimension z and associate it with a calculation that is convenient to you. Here, you can consider the equation related to a circle z is equal to x square plus y square and get a 3-dimensional space. A slice of this space appears as the diagram. What can SVM do with this? SVM draws the best hyperplane. Since this is in 3 dimensions, the hyperplane is a plane parallel to the x-axis at a certain z. Now, map it back to 2 dimensions. Should you need to add this feature manually to have a hyperplane for such nonlinear cases? The answer is no. SVM has a technique called kernel trick. These functions called kernel functions take low-dimensional input space and transforms it to a higher dimensional space, that is, they convert non-separable problems to separable problems. These are mostly useful in nonlinear separation problem. In simple words, these functions carry out some extremely complex data transformations and then find out the process to separate the data based on the defined levels or outputs. Kernel functions are chosen when a model is to be created. While working with SVM, you have to take your set of labeled texts, convert them into vectors using word frequencies, and feed them to the algorithm. The algorithm uses your chosen kernel function to produce a model. When a new unlabeled text needs to be classified, you convert it into a vector and give it to the model, which outputs the tag of the text. These steps of SVM can easily be done in a variety of data science programming languages such as R, Python, etc. using different packages. Besides these techniques, there are some other techniques such as Artificial Neural Network (ANN) and Naive Bayesian model.